Welcome to everyone. It's a pleasure to have Alastair Donaldson. Alastair is a professor at the Department of Computing at Imperial College London, and he's very well known for his work in various aspects of testing, verification, and generally reliability of software systems, programming languages, compilers. And he's probably best known for his work in verification of GPU programs. And today he'll tell us more about this line of work. And today's topic is on trying to clean up an intermediate language for GPU programming. And he'll tell us how he did that. Over to you, Alastair.
Thank you very much, Deepak, and thank you so much for inviting me to speak in this seminar series. It's a real pleasure. The work I'm going to present today is based on a paper that was presented at the POPL conference, Principles of Programming Languages, in 2023. And it was a collaboration with two of my former colleagues at Google, Alan Baker and David Netto, and with my research assistants, Vasilis Klimis and Jack Clark at Imperial, and with my longtime collaborator, John Wickerson, also at Imperial. And in this work, what we were doing was looking at an intermediate language for GPU computing called SPIR-V, which is a pretty ambitious, attractive language for various reasons. But the language had a number of problems in the way it was described in its language specification. There were various problems to do with the way control flow in the language was defined and with some rules governing the correct usage of control flow by programmers. Those rules and definitions didn't quite make sense and didn't do what the language designers wanted them to do. And what we did was use formal methods to try to fix this situation. We came up with a formal model of the control flow part of this SPIR-V language, and we used that formal model as a basis to question the English language specification, conformance tests for the programming language, various tools that have been built to check programs in the language, and we used our formal model as the basis for a discussion with experts. And thanks to this use of formal methods, we were able to rectify problems with control flow in this language and get the language specification fixed. So I'm going to tell you at a relatively high level about how we went about that. May I just confirm you can see my next slide now, the overview slide? Yeah, good. Okay, so the structure of the talk then, I'm going to first of all motivate this SPIR-V language. Then I'll give you an outline to the approach we took to improving the language. After I've given you that outline, I'll then go into what the actual problems with the language were by going through a worked example. And then I'll tell you the basis of our solution, which is called structural dominance. And I'll show you how our solution fixes the problem in the worked example I'm going to show you. And then I'll finish the presentation for telling you about a bonus piece of work that arose from this project, which is a new technique for testing compilers that was quite effective at testing SPIR-V compilers. To motivate SPIR-V, I need to say a little bit about GPU programming. When you program a GPU, when you're a graphics programmer, you write little pieces of code called shaders that run across all of the cores on the GPU. And you write these graphics shaders using a shading language. And there are many of these shading languages. For example, OpenGL has its own shading language. Microsoft have got something called high-level shading language, which is part of their Direct 3D programming model. Apple have a shading language called Metal, and there are various other shading languages. And the job of a shader compiler is to take a program written in one of these languages, a graphics shader, and transform it into machine code that's specific to the particular GPU in your device. So for example, if you have an iPhone like I have here, then you're going to have an Apple compiler that will turn metal shaders down into the machine code specific to whatever GPU is in this phone. And there are many different GPU vendors out there, companies like NVIDIA, Qualcomm, Imagination Technologies, Intel, Apple, ARM. These companies all make GPUs. We often forget this because machine learning means that GPUs are often thought of as being part of AI these days and principally made by NVIDIA, but actually every device with a screen has a GPU, and there are all kinds of companies making GPUs, and all of these companies need to create shader compilers for their GPUs. So there are tons of these shader compilers out there. And the shader compiler is part of the graphics driver for a GPU, and it's by some margin the most complicated part of a graphics driver. The motivation for SPIR-V, the language which I'm going to tell you a bit about during this presentation, is portability. The SPIR part of SPIR-V stands for Standard Portable Intermediate Representation, and the V actually doesn't stand for anything. There was an older version of this language just called SPIR, and the V was added for some reason, I don't know why, to distinguish that old language from the new updated language. But the idea of SPIR-V is that instead of having every GPU maker having a compiler to go from every shading language to their machine code, instead there can be, the current situation is you would have for shading languages A, B, and C, you would have multiple different shader compilers, which is a lot of work for GPU makers. The idea is instead, for different shading languages, A, B, and C, there could be industry standard translators that lower these languages into SPIR-V, and then every GPU maker just has to provide one SPIR-V compiler that can go from SPIR-V down to their GPU-specific machine code. If you're familiar with non-GPU compilers, traditional compilers, this is very similar to the role that an intermediate representation like LLVM-IR plays. You have a few different languages like Rust, C, C++, that get compiled into LLVM-IR, and then there are backends for different devices like ARM or x86 CPUs. So this is like a GPU analog of that situation. And the idea is that SPIR-V is a special intermediate language for GPU computing. So it has various GPU-specific features as first-class constructs in the language. So that's the kind of motivation for SPIR-V. And I'll just pause briefly in case any of you have got any questions about this setting, GPUs, shaders, shading languages, the motivation for SPIR-V. I don't have the, I'm not looking at comments in the chat or at raise hand. So if you do have questions, I'd appreciate it if you could just unmute yourself and ask them.
So there is a question on the chat from Chandradeep. Where does CUDA fit in here?
That's a good question, Chandradeep. Thank you. CUDA, you can think of like a shading language. When we do CUDA programming, we write kernels to run on the GPU, and a kernel is basically the same as a shader. The difference is that CUDA is kind of a special citizen in this domain because NVIDIA have such a huge market share for AI that CUDA has got lots of features that are not really related to graphics. They're more related to general purpose GPU computing. So it wouldn't make sense to compile CUDA down to SPIR-V because NVIDIA, it's really worth them investing in direct compilers from CUDA to their own machine code. So CUDA is a bit of an outlier in this picture. This is much more relevant for actual graphics, things like OpenGL, Direct3D, Metal, Vulkan, graphics APIs for actually making amazing 3D images and 3D rendering appear on your screen. Thanks. Any other questions right now? All right, please do just shout out if there are more in the future. Okay, so SPIR-V is this very promising intermediate language that has seen quite a lot of uptake by GPU companies as a way to avoid redundantly re-implementing compilers for many different shading languages. But there have been some problems in the SPIR-V language related to sophisticated rules about control flow in the language. The idea of these rules is they're meant to help developers write code that compilers will accept and also give compilers a leg up so compilers can do a really good job of optimizing that code when they emit machine code. So these control flow rules in SPIR-V are meant to be a good thing. But before our work, there was evidence that these rules were really not helping in practice. For example, Dmitry Maleshev at Mozilla wrote a blog post called Horrors of SPIRD, which involves some problems related to control flow. Sean Baxter, who's one of the authors of the Circle compiler, has got a blog post ironically titled Targeting SPIRD is super easy and the structurization requirements totally won't make you want to throw yourself off a cliff. There, the structurization requirements relate to control flow. And then Hans Christian Arntzen from Arts and Software also has a blog post called My Personal Hell of Translating DXIL, which is a Microsoft intermediate language, to SPIRD. And again, some of the problems in his personal hell related to control flow. So there was lots of discontent about this language SPIRD, and in particular about the control flow in the language. And in our work, we were trying to get a handle on what those problems were and fix them. So what I want to do is tell you, first of all, at a very high level, the approach we took to this. And I can tell you about this approach without going into any further details of the control flow rules or what SPIRD is. Before we started our work, there were really four main sources of truth about this language, SPIRD. First of all, on the top left here, there was the prose specification, the rules of the language, which is a PDF document, pretty lengthy document explaining in a relatively rigorous way what the language is, what the constructs are, and what the rules governing those constructs are, but not specified in a machine-readable way, definitely not properly mathematically rigorous, just a best effort human way to write down the rules of the language in a reasonably rigorous fashion. Then there was some validation tooling, some tools built by mainly Google, which would take SPIRD programs and check them to assess whether they conform to the requirements of the language specification. Furthermore, there was a set of conformance test suites, examples of SPIRD programs, some of them good examples that are meant to be conformant to the language and are meant to execute to give some particular results, and other negative tests that are examples of bad programs that disobey the rules of the language and should be statically rejected. And furthermore, there are a number of experts on SPIRD in the world, and in particular, David Netto and Alan Baker, who are two of my former colleagues from Google, where I spent some time working, are the two SPIRD experts that we had a very close relationship with. We still do, and in particular, we did at the time of doing this work. So the approach we took was as follows. We did a very careful reading of the control flow rules in the prose specification. And we used Alloy, which is a formal modeling language backed by a SAT-based verification tool, to come up with a rigorous mathematical model of the control flow rules of the language. This model could only be best effort. The reason is that some of the rules in the prose specification were ambiguous, or we thought there were errors in those rules. So what we did is we translated the rules as best we could into unforgiving, rigorous mathematics. Where there was ambiguity in the prose rules, we made a judgment call in encoding this into our model. And we knew before we started the work that there were some known problems with the SPIRD rules. So using our Alloy model, we formulated some solutions to those known problems. And something really good about the Alloy language and tool is you can ask Alloy for positive and negative examples from a model. So if you have a model that describes, say, control flow graphs with particular constraints on their structure, you can ask Alloy to produce graph after graph after graph that satisfy those rules. But you can also ask it to produce a graph that satisfies all of the rules except one and that should violate that one rule. So you can ask Alloy for positive and negative examples according to a model. And we found that was really useful in helping us understand whether some of our ideas to solve control flow related problems in SPIRD were good ideas. When we had ideas for solving some problems with the language, we consulted our friends David and Alan about those solutions. And the thing is that David and Alan have a really good oversight of what the GPU community actually want from the programming language. These rules don't exist in a vacuum. They exist to try to serve programmers and compiler writers. So when we had an idea about reformulating a rule that might clean up some problems, but might, say, make certain programs disallowed that were previously allowed, Alan and David would have a good idea as to whether that would be acceptable to the community or not. Once we had got an alloy model we were happy with, we then did some cross-checking against the existing conformance tests. We could use our model against every test in the conformance test suite. When the test was a valid program, we could ask, does our model say it's valid? And when it was an invalid program, we could ask, does our model agree that it's invalid? And during this process, we found various bugs in the conformance test suite. So we were able to contribute fixes to some conformance tests that just turned out to be wrong. And we consulted with our expert friends in deciding whether these tests really were wrong. And furthermore, we found plenty of bugs in our model during this process. The conformance tests made us realize that we'd overlooked details captured by the conformance tests that either weren't captured by the original prose specification or that we'd overlooked. The next thing we did is we used Alloy to automatically generate a huge number of interesting control flow graphs, some of which were valid and some of which were invalid. And critically, our model was able to tell us these ones are valid, these ones are not valid. We were then able to feed those examples to the existing validation tooling, this really efficient tooling written in C++, and ask, does the validation tooling agree with our model about whether these examples are valid? And once again, we found numerous bugs in the validation tooling, and our expert friends at Google, who were largely responsible for making this validation tooling, were able to confirm when these were bugs, and largely they made fixes to the tooling. And once again, we found plenty of problems in our model by cross-checking our model against the validator. So we updated our model. And then we had a virtuous cycle where we kept cross-checking our model against the conformance tests, cross-checking our model against the validation tooling, and consulting with our expert friends, until eventually we got to a point where our model agreed with the conformance test suite about validity of programs and agreed with the validation tooling, which had been improved on the validity of programs. And our experts agreed with changes we made in the model to make it consistent with the conformance test suites and the validation tooling. So at this point, we had a very precise mathematical model of SPIR-V control flow that we'd engineered thanks to consultation with our expert friends, cross-checking against these tests and cross-checking against this validator. And we were able then to go back to the prose specification and substantially rewrite the part of the specification related to control flow using straightforward English that engineers can understand, but very precise English that captured the precision of our formal Alloy model. And these changes were accepted by Kronos, which is the industry consortium who manage this language, and they are now incorporated into the language specification. So we ended up with agreement between all of these different sources of truth. So that's a high-level overview of this project, and I'd love now to take any questions on that before I go into some of the...
Yeah, so Alastair, there are a couple of questions. One is, I think Raghavan wants to know what is invalid and valid control flow, but I guess we'll come to that later, maybe.
I'm actually not going to go into too much detail on invalid and valid control flow,
Okay.
but I'm going to more go into some of the problems with the definitions of control flow. But let me just give you a couple of examples. In SPIR-V, a loop can only have one exit point. That's an example of a rule on control flow graphs. So SPIR-V has a special notion of loops in control flow graphs, which I'll show you in a minute. And one rule, it says essentially that any branch out of a loop has got to go to the loop's designated exit node. So that's just one example of a rule. The rules are very detailed, and I feel like they're super interesting if you're actually working on SPIR-V. If you're more generally interested in formal methods and compilers, the specifics of the rules I don't think are so interesting, so I'm not going to go into them in the talk. But in the Popple paper, we have a bunch of examples of the rules.
Okay, and there's one more question from Pramod. How did you translate the conformance tests into Alloy?
What's the question? How did we transform the conformance tests into Alloy?
Yeah.
What we did was, first of all, our Alloy model only assesses whether a skeleton control flow graph is valid or not. It doesn't care at all about the instructions inside the control flow graph. So what we did is we wrote a tool, which we called SPIR-V to Alloy, a very simple tool that would take a SPIR-V program, extract its control flow graph skeleton, and turn that into the language of the Alloy analyzer. And then Alloy was able to check, does this description of the control flow graph agree with the constraints that are our Alloy model? So our model is a bunch of constraints, and we were able to extract a graph description from a conformance test and ask, does this graph match those constraints? Does it satisfy those constraints? So we had a simple tool that would go from a SPIR-V program to an Alloy graph description. And we had a script that ran that over the whole conformance test suite. So the question, anything else at this point?
So I had one more question. This is Raghavan. So is the Alloy model the final deliverable of your project?
Actually, no. Interestingly, at the end of the project, the final deliverable is the improved specification. And we could, if we want, rip up the Alloy model. So in some sense, the Alloy model was an unforgiving mathematical instrument that allowed us to get consensus between all of these less rigorous sources of truth. But once we had gone around this cycle of improving the test suite, improving the validator, fixing up the model, talking to the experts, once we've done that several times, we got lots of benefit from that, better tests, better validation tooling, and a better specification. And now actually the Alloy model is basically defunct because there isn't a plan to try to keep changing SPIR-V, the language. So the Alloy model has basically done its job now. It still exists. A couple of times Google have come to us and said, hey, could you run this by the Alloy model to see whether this is allowed? And then they've been happy that, it is. But we're not exposing the Alloy model to engineers as something they would directly interact with. They could, it's open source, it's available, but it's something you would need some verification expertise to work with. Does that make sense?
Okay, thanks.
Yeah. It's different. For example, there's a project, I think it's called JS-CERT, which is about mechanizing the JavaScript API or the JavaScript language. And I think in that project, they actually have a one-to-one correspondence with some formal description of JavaScript and the English language spec. And I think that correspondence is automatically maintained over time. And if the spec gets out of sync with the formal model, some continuous integration fails somewhere. So we don't have anything like that in this setting. So if someone would come in and start wrecking the SPIR-V specification, we wouldn't know. Yeah. Okay. So what I want to do now is go in a little bit of a deep dive into some of the problems with SPIR-V. Basically, just want to give you a flavor of the kind of intentions of the specification before our work, but some of the ambiguity that led to problems and some of the attempted fixes in the specification that, in my opinion, only made things worse. And then I'll show you our solution, which has actually turned out to be really simple, as is often the case in computer science. Once you sort of struggle with various complicated solutions, and then eventually you come up with a really simple, elegant solution and think, hang on a minute, why didn't we see this from the beginning? What I'm showing you here is a high-level program that is written in GLSL, the OpenGL shading language. This is not meant to be representative of a realistic graphics program. This is just a toy program that does some integer computation, but it serves to illustrate a couple of points I want to make here. Now, the comments where I've written %1, %2, etc., they're going to be relevant when I show you a SPIR-V representation of this program. So we have a main function that declares a couple of variables. Then we have a while loop that's going to iterate 100 times. And we have a condition in the loop body that's going to increment x by different values depending on the value of I. If we would run this through a standard translator into SPIR-V, we would get something like the code on the right. We've got things like op label, which is an instruction saying that this instruction starts a basic block. We've got instructions like op branch, which is an unconditional branch, op branch conditional, which is a conditional branch, saying that if a condition is true, go to block 3, otherwise go to block 8. And then we've got a lot of arithmetic and memory-related operations, which are grayed out, like op load, op signed less than. And those don't matter for the purposes of this talk. Then we've got some special operations, these things called loop merge instructions, selection merge instructions. These are used in SPIR-V to declare that particular blocks are the headers of loops or of selection constructs. So this block 2 here that I'm hovering over with the mouse, can I just confirm, by the way, can you see my mouse pointer on Zoom?
Can you move it a bit?
I'm moving it around the screen now.
No, I can't see. Okay, I don't. Yeah, I can see. I can see where like an arrow shape.
You can't see it.
It's
That's
very
fine.
small. It's very
Yeah,
small.
It's very small. Okay. Just give me 1 second because it would be nice if I could use it. So I'm just going to see whether there's in the meeting controls whether there's a way of making this bigger. So sorry, just bear with me for a moment. I think this could be a good investment of time if it works. Although I must admit, I'm not very good with Zoom, despite everything we went through with COVID. No, I can't figure it out. Never mind. Okay, I'll just talk. So rather than try to wave my pointer about, but good to know. Okay, so block 2, the second block you can see on the right-hand side, starts with op label saying this is a basic block. And then the second last instruction says op loop merge. And then it says 8, which I put in green, and 7, which I put in orange. And what this means is this loop's exit block is block 8. And furthermore, block 7 is the continuing construct for the loop. Block 7 is the start of a construct that is going to be executed right before every subsequent loop iteration. So this is one way this program on the left could be represented in SPIR-V. Now, what I'm showing you here on the left is the SPIR-V instructions, which I've demarcated into basic blocks. And we can view that as a control flow graph in the standard way. So on the right-hand side, I've got a control flow graph where in each node, I've included the ID of the op label instruction for the block. So you can see the first node in the graph on the right is %1, because on the left, we've got %1 equals op label. And you can see that on nodes 2 and nodes 3, I've annotated them with the merge block, which is 8 for block 2 and 6 for block 3. And in the case of block 2, which is a loop, I've got the continue block, which is block 7. And rather than using this text inside a block to indicate its merge and continue, what I'm going to do is use a dashed green edge to say what the merge block is for a loop header or a selection header, and a dotted orange line to say what is the continue block for a loop. And what I want to emphasize to you is that on the graph on the right, the dashed edges, the dashed and dotted edges, those are not control flow edges. The control flow is only indicated by the solid edges. And the dashed and dotted edges are metadata saying this loop is guaranteed to reconverge at block 8. So, or this conditional is guaranteed to reconverge at block 6. Or this loop, before it goes back to the loop head, is guaranteed to execute block 7. Okay? So the solid black edges are the real control flow edges. And those dashed and dotted edges, those are edges indicating this merge and continue metadata. Right. Now in SPIR-V, there's this thing called a selection construct. And intuitively, that's meant to model the body of an if-then-else statement, but at the control flow graph level. So if we look at our little example expressed in high-level code, where we've got if I less than 50, increment x by 2, otherwise increment x by 4. If I go to the right-hand side, intuitively, we would like this region of blocks to be that selection construct, right? We would like 3, which is the entry point to the if-then-else, 4, which is the then branch, and 5, which is the else branch. We would like those 3 blocks to be the selection construct corresponding to the if-then-else. And then you can see that the then and else branch, they reconverge to block 6, which is the merge block for the selection construct, which is indicated by the dashed green edge from 3 to 6. So intuitively, that's what we would like. So now let's look at the way SPIR-V defined selection construct prior to my group's work. In order to give this definition, I need to remind you about the notion of dominance, which I'm sure many of you are familiar with from compilers, but just in case, here's a reminder. A block A is said to dominate a block B if every path from the entry of the control flow graph to the block B goes through block A. So for example, what blocks are dominated by block 3 in this example? Well, certainly 3 dominates itself, because to get to 3, you need to go through 3. And 3 dominates 4 and 5 because you can't reach 4 or 5 without going through 3. And similarly, 3 dominates 6 and 3 dominates 7 because if you want to reach 6 or 7, you must go through 3. So 3 dominates 3, 4, 5, 6, and 7. Those are the blocks dominated by block 3. All right, so that's just a reminder, in case you've not studied it for some time, about the notion of dominance, which is standard in the compiler's literature. And here, a control flow path is just the solid black edges. We can ignore the dashed and dotted edges for now. Okay, so the definition of a selection construct in the SPIR-V specification before our work was as follows. It said a selection construct includes the blocks dominated by a selection header while excluding blocks dominated by the selection construct's merge block. So let's look at what this would mean with respect to block 3. So block 3 is a selection header. What blocks does it dominate? Well, 3, 4, 5, 6, 7, as we just went through on the previous slide. What is that selection header's merge block? It's block 6. That's what the green dashed arrow means. What nodes are dominated by 6? Well, it's 6 and 7, okay? Because 6 dominates itself, and you can't reach block 7 without going through block 6 using solid edges of this graph. So we remove 6 and 7 from the nodes dominated by the by the selection header 3. And that gives us exactly what we intuitively would like, okay? So as I argued before, the high-level program on the left had an if-then-else, and in the IR, we'd like that to be modeled by a selection construct. We'd like it to be the blocks 3, 4, and 5, and that's exactly what the text in the SPIR-V specification gave us. So everything works really well there. This is the original text defining a selection construct in SPIR-V. Okay, but now let's say we fiddled with our program so that our if-then-else inside a loop here. So I've changed this program to have a do-while loop. And in the do-while loop, we're saying if I is bigger than 50, break. Otherwise, do nothing. So if we take this changed program where there's a break from inside the if statement, we now get the control flow graph I've shown you on the right here. And in this control flow graph, intuitively, we would like blocks 3 and 4 to be the selection construct, okay? Because you can see 3 on the left-hand side, I've said, well, that's the head of the if-then-else, and 4 is the block representing a no-op, and the break doesn't have a block. But what would the specification tell us here? It would say to us, it's the blocks dominated by 3, well, that's 3, 4, 5, 6, and 7, minus the blocks dominated by block 3's merge target, i.e. minus the blocks dominated by 5. Well, what does block 5 dominate? 5 dominates 6 and 5, right? 5 dominates itself and 6. But 5 doesn't dominate 7. The reason is that you can get to block 7 by going 1, 2, 3, 7. You don't need to pass through 5. Therefore, 5 doesn't dominate 7. So we end up saying that the blocks 3, 4, 7 comprise the selection construct headed at block 3. But 7 is the end of the program, and that doesn't make any sense. It doesn't make sense for the block at the end of the program to be part of the if-then-else statement shown in the code on the left. So I hope if you've been following this in detail, the key thing is that the rules really don't give us what we want here, okay? And if you haven't been following it in detail, just trust me, the rules here come up with something nonsensical. We've got a block that's not inside the if-then-else that is being regarded by the rules of the language as being part of the construct that if-then-else defines. So this really shows that the rules are not doing what the language designers wanted. The language designers were aware of this example before our work, and what they did is they tried to fix it in the following way. So this is the original definition of a selection construct. And knowing about a problem like the previous example, they added the following text. Furthermore, these structured control flow constructs are additionally defined to exclude all outer constructs, continued constructs, and exclude all blocks dominated by all outer constructs merge blocks. Wow, that's a bit of a mouthful. And furthermore, it's a bit circular, right? Because we're saying that a structured control flow construct is defined to exclude other structured control flow constructs. So the definition of a structured control flow construct relies on the definition of a structured control flow construct. So the two problems here are this extra language is complicated. I find it hard to understand. And furthermore, it's a bit ambiguous because it's somehow circular. So it really doesn't seem like a very good way to make the first paragraph, which was the nice, clean, but slightly wrong definition. It doesn't seem like a good way to make this definition correct. Okay, so I'm going to now talk about structural dominance, which is the ultimately really quite simple solution we came up with to this problem. Before I do that, does anyone have any questions about the technical examples of the last couple of slides? Happy to go back if any of the details didn't make sense.
So did this problem come about? I mean, the earlier definition was not working because of this unstructured control flow, or was it because I had a break in between the loop?
I'm sorry, but the audio quality is really bad. I wonder if you could just repeat that
Sorry.
slowly.
Yeah, sorry, my mic is... Yeah, so I'm just wondering whether the original definition would have been fine if you didn't have a unstructured control flow in your original program, like the break inside the loop.
Yes, if in the original program, so let me just go back briefly. In this example here, where we didn't have any non-local control flow, so there was no break in the loop. In this case, the original definition worked perfectly. Okay? Mm-hmm. Whereas when we then made the example a bit different to involve a break inside a loop, the original definition breaks down and gives us something that we don't want. So the way I don't know the history of how the language was designed, but my guess is that when the rules were being designed, people had nice, clean examples like this one in mind. However, they do want to support these slightly less straightforward examples. That absolutely is a design goal of SPIR-V, and the original definitions don't work for these slightly more complicated examples. Hence why the language designers tried to add this extra language to try to solve the problem. But as I've argued, I think this extra language is rather complex and rather circular. Yeah. Any other questions, Dan? Okay, so the solution we ended up coming up with, after trying various other more complicated solutions, is actually very simple. Remember that a control flow path, a path, let's say, is a sequence of the solid black edges. Well, in our work, what we do is we define a structural path, which is a path comprised of any combination of solid, dashed, or dotted edges. So a control flow edge, solid, a merge edge, dashed, or a continue construct edge, dotted. And then what we do is we define structural dominance to be the same as dominance, but using structural paths. So remember that a block A dominates a block B if every path from the entry to the control flow graph to B includes A. And analogously, we can say that a block A structurally dominates block B if every structural path from entry to B includes A. So for example, the nodes dominated by block 3, as we looked at previously, are 3, 4, 5, 6, and 7. However, the nodes structurally dominated by 3, well, let's work it out. 3 structurally dominates itself, okay, because every path to 3 goes through 3. And also, if you look at blocks 4 and 5, then it's clear that 3 structurally dominates them, because there's no way you can get to block 4 or block 5 by following a sequence of solid dashed or dotted edges without going through block 3. And the same holds for block 6. So block 3 structurally dominates blocks 4, 5, and 6. However, block 3 doesn't structurally dominate 7 because of the structural path 1, 2, 7. That path is not a control flow path because there is not a control flow edge from 2 to 7. However, there is a metadata edge, a structural edge from 2 to 7, because 7 is defined as being the continued construct of block 2. So the nodes that are structurally dominated by 3 are just the nodes 3, 4, 5, and 6, not this node 7. And what we did is we redefined selection construct simply to use structural dominance instead of dominance. So the original definition said that a selection construct includes the blocks dominated by a selection header. Well, we changed that to be structurally dominated, but excluding the blocks dominated by the merge block of the construct. Well, we changed dominated there to be structurally dominated. And what we found, and this is one example of many examples of rules, because there are other kinds of constructs in the spec I'm not going to go into today. This is one example of a bunch of rules that we could fix by using structural dominance rather than standard dominance. And we were able to eliminate lots of this extra language that was trying to patch up the specification to cope with edge case scenarios and arguably not managing to do so by not being sufficiently precise. So we were able to fix the spec and substantially simplify it. To go back to the loop with an early break example, let's ask again with our new definition, what is the selection construct headed at block 3? Well, it's the blocks structurally dominated by 3, which is 3, 4, and 5. Note here, we don't have 6 and 7 because with 6, we've got an edge 1, we've got a path, a structural path 1, 2, 6 that doesn't go through 3. And with 7, we've got a structural path 1, 2, 7 that doesn't go through 3. And then we take away any blocks that are structurally dominated by 3's merge block. In particular, we take away block 5. And what that gives us is just the blocks 3 and 4. And that's exactly what we would like here. We would like the structured, the selection construct headed by block 3 to comprise blocks 3 and 4, because intuitively, these are the blocks making up that if then else statement that's got the early break. Okay? So in the paper, there are lots more details about this. We give a whole collection of problems with the initial specification. Then we go through structural dominance formally, and we show for each of the problems why structural dominance fixes the problem. The SPIRD specification has been updated. We worked hard with the Kronos group who managed that specification to incorporate fixes based on our rules. They accepted those. And then the SPIRD validator has been updated to check those rules based on structural dominance. And as I mentioned earlier on in the talk, we occasionally consult with Google regarding follow-on issues. Actually, these slides are from shortly after we first did this work in 2023, and I think we haven't had a request from Google to consult regarding our model for some time now. But for a while after we did this work, we had some requests from Google asking for our model's opinion on whether particular graphs were valid or not. Okay, so that is the end of the material about the way we improve this language specification. And the final piece of my talk is about a bonus bit of work, which is to do with a new method for testing compilers based on the control program.
Alastair, if I can ask a question on the previous part, sorry to interrupt.
Yeah, please.
So where was the validity constraint regarding the selection construct? I mean, you just changed the definition of a selection construct, but how was it used in a validity constraint?
Yes, so in the specification, there were definitions of selection construct, loop construct, switch construct, okay? And then there were a whole load of rules governing how it's legal for control to exit those constructs. There were lots of exit rules. So first of all, the rules were all flawed because the definitions of the constructs were not sound. Right, so loops, conditionals, and switches, they weren't properly defined in the first place because of deficiencies like the one I illustrated to you there. And then in addition, all these exit rules in the specification, they also suffered, not universally, but a number of those exit rules suffered from inaccuracies, or they had lots of exceptions to try to handle weird edge cases. And what we found was that our structural dominance definition totally cleaned that up. And in the POPL paper, we go through a number of examples of rules that could be fixed up. I don't have an example of a rule to hand. And a challenge for me in presenting this work, I really like this project. It's one of the pieces of work I'm the most proud of. but it's very, very, very much like the devil is in the detail. So to give examples, you sort of need to go through lots of control flow graphs, and I question how interesting that would be for a general talk. But in the paper, we do have a ton of those examples, and if you'd like to talk about them offline, I'd be delighted to get back into it.
Okay, thanks.
I had a question, Alastair. What was the role of alloy? So did you fix the specific? Did you find out the problem in the specification using alloy, or did you fix the specification using alloy, or was it? It's not clear to me what was the manual work and what was the help given by alloy in this process.
Yeah, let me speak to that. It was really an engineering project using alloy as an engineering tool. So, for example, we had some proposals for fixing these problems before we came up with structural dominance. I actually don't remember quite what those proposals were, but what we did is we modeled them in alloy. And we thought, I think this is equivalent to what the spec currently says, but it fixes these problems. Let's ask alloy for lots of distinct examples that satisfy our rules. So what alloy does is it uses a SAT solver to synthesize examples up to a given bound that satisfy the constraints that you've written down. So then we could study those examples, sometimes manually, sometimes by passing them through the existing SPIR-V validator. And when they were examples that no longer were accepted, we would look at those examples and think, are we okay with that? Is it reasonable to exclude control flow graphs of this shape for the sake of this simplicity of definitions, or by fixing this problem with a specification? Is this excluding these other examples? Is that fine too? Those examples are also bad. Or is this actually a sign that our solution isn't really workable? So when we came up with structural dominance, we used structural dominance to check rigorously via alloy whether examples that were previously disallowed are still disallowed, whether examples that were deemed good and were previously allowed were still allowed. And we came up with a very small number of edge cases that were previously allowed, but our simpler, more elegant approach didn't allow them anymore. And alloy did the checking of that for us automatically. And then we talked to Google, and the folks at Google and the Kronos group agreed eliminating these acceptable but rather strange examples would be a price worth paying for having a simpler set of rules. Okay, so we weren't using alloy to formally verify our definitions. We weren't using alloy to give a kind of conclusive proof that what we were doing was correct. We were rather using alloy as a consistent daemon that would give us examples we would never have thought of ourselves as humans that violated our rules, or examples that we would never have thought of that were allowed by our rules that maybe shouldn't be allowed. So it was really using alloy as an engineering aid.
Yeah, I got that. It was a very nice presentation. So one follow-on question was, did you encode the previously known examples that you want to allow and the previously known examples that you don't want to allow also as alloy constraints, where the individual examples also encoded into alloy?
Yes, what we did is we had a number of examples that we, what we did is we basically had a Google Doc that we shared with our friends at Google, where we drew loads of examples that we knew already before we started the project. We don't want this to be allowed. We don't want that to be allowed. And then we iterated on that Google Doc for a while. Then we coded those up as alloy constraints. So with alloy, the way you describe a graph is to give a set of constraints that has exactly one solution, which is the graph you want. So those examples, good and bad, we coded up manually. Then I mentioned earlier, we had that tool called SPIR-V to alloy that would go from a SPIR-V program to an alloy graph description. And we ran that over a very large number, thousands and thousands of examples in the conformance test suite that were labeled mainly as good, but occasionally as bad. And we checked whether our model still agreed with those. And when it didn't agree, we manually investigated what the problem was. And we either fixed our model or we went to the owners of those test suites and said, hey, look, this has been in your test suite for years, but actually we think it's wrong. We think it should not have been allowed in the first place, and had a discussion about that.
Got it. Thank you.
Pleasure. Okay, so I have one more component of the talk, but I realize I've been talking for quite some time. It'll probably take me about 5 minutes to go through this. I can do that, or we can just stop here.
Yeah, no, that's fine. Yeah, go ahead. Yeah.
Okay. So what we had was our alloy model was able to produce weird and wonderful SPIR-V control flow graphs. And we built a tool called SPIR-V to alloy, like I mentioned before, that would turn these into, this slide should say alloy to SPIR-V. This is the other direction. Alloy to SPIR-V would go from alloy into SPIR-V control flow skeletons. But the trouble is, the bodies of the blocks of those control flow graphs were empty. So you couldn't run the programs produced by our alloy model. You could ask, are the graphs valid according to the SPIR-V validity checker, but you couldn't actually execute the graphs to get a computation going. What we felt this was a shame because we had this amazing collection, like a zoo of difficult to compile control flow graphs, and there are a load of SPIR-V compilers out there, and we thought it would be great to use these graphs to test those compilers, but we can't actually turn them into runnable test cases, or rather they aren't runnable test cases. So we had a very simple idea for turning them into runnable test cases, which we call fleshing. This is a super simple idea. The idea is you take a skeleton CFG and you instrument it so that A, it's guaranteed to follow a path dictated by its input, and B, you get it to record the IDs of the basic blocks that were actually traversed during execution. And you check that the path that should have been followed really is followed. I'm going to illustrate with this with an example in a moment, but it's a super simple idea. And what we found is that it allowed us to find 20 previously unknown bugs in SPIR-V compilers, many of them miscompilation bugs, where the compiler had not crashed, it just produced wrong machine code. So to give you an example, let's say we had this control flow graph with entry point 1. What we do is we instrument the graph with an output array and an index into that array. If you visit block 1, then the value 1 gets written to the output array, and the output array index gets incremented. And the same for all the other blocks. If you execute block 2, the number 2 gets written to the output array. If you execute block 6, the number 6 gets written to the output array. So let's imagine the output array has got plenty of space. Any execution through this graph is going to lead to the output array getting filled up with the IDs of the blocks that got visited. What we also do is whenever a block has got a choice as to its successor, so whenever a block has got a conditional branch, we read the condition from an input array. So at block 1, we're saying we're going to read a Boolean C from input array at index J, and then we're going to increment J so that we can read from a different index of the input array later. And then we're going to branch depending on what was read from the input array. So if we read true from the input array, we go to block 2. And if we read false from the input array, we go to block 7. And we do this for any block that ends with a conditional branch. So block 3, for example, unconditionally branches to block 5. So we don't need to consult the input array. But if we look at block 4, you can see at block 4, we can branch either to block 5 or to block 7. So the block is fleshed to query the input array using index J to ask, should I go to block 5, which is what will happen if C is true, or should I go to block 7, which will happen if C is false? So this is a really, really simple way to turn a control flow graph into something that is executable such that inputs map to expected outputs. In particular, if we run this program with the input 11110, 1111, 11110, 11100, then we're going to go from block 1 to block 2, from block 2 to block 3, etc., etc. I won't work through all the details, but if you would work through the details, you should expect the output array to contain 1, 2, 3, 5, 6, 1, 2, 4, 5, 6, 1, 2, 4, 7. The program would terminate when block 7 is reached. So if we would run the program on that input array and then inspect the output array and find that it doesn't contain 1, 2, 3, 5, 6, 1, 2, 4, 5, 6, 1, 2, 4, 7, then we know that the program must have been miscompiled. Any other answer can't be correct because this very simple program has been fleshed to follow exactly the path that was requested by the input. So this technique was something we came up with just to try and squeeze some extra juice out of our project. We had a way of getting these very strange control flow graphs, and by fleshing them into runnable programs, we could test SPIR-V compilers. And as I said, we found a number of bugs using that approach. So in summary, we've done formal modeling of this SPIR-V language at the control flow level that allowed us to identify and fix some fundamental problems with control flow. These changes have been adopted by industry. They're now done and dusted in the SPIR-V specification. And our solution, structural dominance, ended up being pleasingly simple, perhaps obvious in hindsight. I wouldn't be surprised if you thought, what an obvious idea. Why did no one think of that before when I presented the idea of using those other edges in the dominance relation? But the fact is that the folks who made the language didn't think of it, and it took us a long time to think of this simple idea. So often I think good, simple ideas are obvious in hindsight. And because our alloy model can generate difficult CFGs, we came up with this approach of fleshing those into runnable programs, which as a byproduct of our work was useful in triggering compiler bugs. One thing I'd be interested in looking at is whether this structural dominance has broader relevance in other intermediate representations that have some notion of structured control flow, and whether fleshing could be used to find bugs in other compilers for different languages. And in fact, I've had a project with one of my current PhD students on using fleshing to find bugs in decompilers rather than in compilers. So that brings me to the end of my presentation. I've appreciated all the questions so far and very keen to chat for as long as you want to, if you've got more questions. Thank you very much.
Thanks a lot, Alastair. Do you all have any questions?
Yeah, Raghavan, I still have a couple of questions.
Sure.
The last part of that, the last thing you said, Alastair, is does it test? It's very interesting. Does it test only that the compiler preserves control flow paths? The control flow path could be preserved, but other semantic aspects could still be wrong. Is that
essentially yes? So the programs that we flesh, all they do is ask where they should go next and record where they went. That's all they do. They're very boring programs. They're programs that would just say, block 1 got visited, block 5 got visited, block 8 got visited, block 12 got visited, right? That's what they write to the output array. And when they come to a branch, they ask the input array, should I go left or right? Okay, that's all they do. Slightly more complicated because we handle switches. So actually the input array contains integers, because in the case of a switch, you could go to many successors. These programs are super simple. They would not find a compiler bug related to division or multiplication, because they don't do any division or multiplication, okay? So the scope of bugs this technique can find is super limited. But any optimization on one of these graphs, even if it merges blocks, etc., it shouldn't change those writes to the output array, right? If it merges 2 blocks together where one block said, I'm block 4, and the other block said, I'm block 5, you should get a merge block that says, I'm block 4, I'm block 5, okay? So it's a way of detecting cases where the compiler has basically tripped up and mangled control flow in a bad way. And it was effective at finding a number of those bugs. It would not be effective at finding other sorts of bugs, like bugs in a peephole optimizer, because there's no scope for peephole optimizations in the programs that we generate here.
Thank you.
Yeah, this Pramod. So, towards the end you said you checked whether this fleshing idea can be used in what compilers for which language?
You mean on the last slide, I was asking whether structural dominance might have broader relevance. Is that what you were?
No, about the fleshing.
Oh, the fleshing. Yes. Well, yeah. Fleshing hasn't got anything to do with structured control flow.
Correct.
Okay, so you could, given any CFG, you could flesh the CFG. So you could have, say, an x86 assembly program. You could encode a CFG in x86 assembly, and you could flesh it and try and use this technique to test the decompiler. You could take an LLVM IR program and flesh it and use it to test LLVM, right? With something like Java bytecode, it's a bit less clear what you do because, no, sorry, Java bytecode also works because arbitrary control flow is supported in Java bytecode. If your language is more restricted with respect to control flow, like WebAssembly, for example, then you'd have to apply the idea in a more restricted setting. So basically, we didn't think about control flow fleshing as a way to test compilers in general. It was more like a bonus that arose from our work. But there's no reason one couldn't use it to test other compilers. Okay. However, we have since this work done a bit of I had a student project where someone tried control flow fleshing for other compilers and it wasn't effective. It's been effective for D compilers. My hypothesis there is SPIR-V control flow is something compilers have had difficulty with, partly because control flow on GPUs is complicated because of things like warp convergence, which some of you may know about. Secondly, the SPIR-V control flow rules before my group's work were a bit of a mess. So compilers, unsurprisingly, might not be doing the right thing because the right thing was potentially ambiguous. D compilers, they have to do control flow recovery. They're trying to recover high-level structures from arbitrary control flow graphs. So if you give them crazy control flow graphs, that can be a good way to provoke bugs in control flow recovery. But if you think about something like LLVM, taking a control flow graph and lowering it to x86 machine code, that's like LLVM's bread and butter. That's exactly what it's designed to do. So it would be pretty surprising if fleshing would find a bug in a mature compiler framework like LLVM.
Okay. So in a way, the arbitrary long strings of zeros and ones are the input to this program it would generate, and you would run that, right? So in a way,
sorry, the audio isn't very good. You just repeat the question.
Yeah. So I'm saying you're generating a strings of zeros and ones which decide the direction of the branch.
Yeah.
And very long strings of zeros and ones are kind of you're somehow incorporating looping in them, right? If the CFG has some kind of a loop, it embodies a loop in some form. So there might be just one smallest string of zeros and ones which capture the executions, a large part of the executions is what I would say. Is that a fair?
Yes, what we did was we give it a graph. We had a randomized way of choosing a path from the entry point of the graph to one of the exit nodes of the graph. And that algorithm would have some probability of traversing loops multiple times. So it would produce a fairly long input that may do multiple loop iterations. After we find a bug, the first thing we would do, but this was manual, we didn't have an automated way of doing this. For our decompiler testing project, we since have built an automated way of doing this. But once we found a bug, the first thing we would do would be ask, if the path involves going around a loop several times, could we just remove the segment of the input that would lead to some of the loop iterations? And would we still trigger the bug?
Correct.
So we would come up with a simpler and simpler path.
Yeah. So okay. So I'm just saying the other way around. I mean, you generate a set of strings and then you feed it that to the graph. Set of zeros and ones. You're working the other way. You're looking at the graph and then deciding whether this branch is taken or not randomly.
Yes, that's right. We look at the graph. We decide what path we want the program to traverse. And then we synthesize a sequence of zeros and ones that will force that path by construction.
Correct. So I'm saying, what about the other way around? You generate which is generate a string of zeros and ones, and then feed it to and feed that to the CFG. And so that way you get a set of inputs which will decide whether the program is going to work or with those. As in which of those strings it is going to accept, right? Is that
if you generated a sequence of zeros and ones, you could run the program on that sequence of zeros and ones.
Correct.
However, if the program didn't reach the end of the graph, then the program would need to eat up more zeros and ones. Okay. So if you generated a very long sequence of zeros and ones, then probabilistically it's likely that eventually the program would terminate because it would reach an exit node and it wouldn't consume the remainder.
Correct.
Okay, and then you could ask, okay, for that sequence of zeros and ones, what should the program have produced by inspecting the graph, and what did it really produce by inspecting the program's output? That would work as well. That's not the way we did it. Unless I've misunderstood your idea, I think that's kind of just a different implementation choice for the idea. I feel like it's the same.
Yeah, it is.
The same.
Yeah, I agree. It's similar, but I think it would generate you more test cases because you're arbitrarily generating strings rather than looking at the graph, right?
Yes, I see what you mean. However,
yeah, anyway, this is just something which occurred to test.
Yeah, thank you. I've got to think more about that. I think that's a really interesting point.
But Pramod, wouldn't you generate some invalid paths also? Because I mean, like some node may not have a branch, and you'll say 0 or 1.
Yeah, so that you would have to incorporate in that array, which will say that okay, so this doesn't make sense. So, there should be a way to flag that in your output array, right?
Well, our program only eats up an input element when there is a branch.
Yeah.
So actually, that would be okay. The problem feedback would be if the sequence of zeros and ones was not long enough to drive the program to a final node of the graph, then the program, I guess, would crash because it would try and read past the bounds of the input array. But that could be dealt with either pragmatically, just by giving it a gigabyte worth of zeros and ones, hope that it terminates, right?
Right. That's interesting.
If we have time, I had one more question.
Sure.
I also have one question.
Yeah, go ahead. Both Raghavan, go ahead, then Ashish can go ahead.
Okay. So the notion of the structural metadata edges, is that a novel idea in your work, or was it pre-existing, and does it have other applications? I find that notion quite interesting, those meta edges.
Yeah. Well, the SPIR-V language introduces this idea of a loop header having a designated merge node and a loop header having a designated continue node, and similarly for selection constructs, which have a designated merge node. In the SPIR-V specification, it describes that a block that is a loop header must have this special instruction called a merge instruction, saying what the merge node is and what the continue node is. The specification doesn't say these are edges in a graph. However, before I got involved in this, there was already a tool called, I think it's called SPIR-V CFG, that turns a SPIR-V program into a dot file, the graph package dot, showing you the control flow graph. And that tool already had the idea of showing you the relationship between a header and its merge using a dotted or dashed edge. So that idea is a SPIR-V idea, and the idea of thinking about it as edges was not my idea, my group's idea. Our idea was thinking, why don't we use those edges as part of the dominance definition to really indicate, in a sense, this node and this merge point have an official relationship with each other. It's not just indicated by the metadata, it's kind of an official relationship that influences the dominance relation. So that was our
And would this idea be applicable only in SPIR-V, or would your redefined dominance have uses in general, any language with bricks and continues? Or is it SPIR-V specific?
Yeah, so I haven't seen a similar construct in other languages, but I think the construct is useful if you would like to have a language that gives you the benefits of high-level program constructs and the flexibility of control flow graphs. Okay, so if you think about a traditional compiler like GCC or LLVM, it's just once it's lowered the program into IR, it's just dealing with a spaghetti of nodes, and it does things like using dominance and back edges to reconstruct natural loops in the control flow graph. And all the information about the original high-level program structure basically gets lost, and then optimizations might need to recover it. if you think about a language like Java, where you've got quite strict nesting in the source code level, that in some ways is quite restrictive. So the idea of SPIR-V is to give you a control flow graph based representation, which has some benefits, but to allow high-level structural information to be baked into the control flow graph in a way that compilers can take advantage of. So I think that structural dominance could be useful in other languages that want to achieve that sweet spot. However, I don't know of any other languages that are trying to achieve that goal, right? So I've heard people talk about a variant of MLIR a variant of LLVM that's got structural constraints. And I've often thought, hey, maybe I should look into that and see whether these ideas would be relevant. But it's not something I've come across in other languages. Please let me know if you know of any.
Ashish, you had a question?
Yeah. Thanks for the talk. So I have a question which you might have answered initially. I was 5 minutes or some late. So if I understand correctly, the formal modeling, the alloy modeling is done manually.
Yeah.
So my first question is like, how big was that task? Like, how big was that specification? The other question and the related thing is, so there is also this validator, if I remember correctly, you showed. And that validator also does some kind of static validation of the thing. Was it a model-based thing, or it was more dynamic in some sense? And were you able to use some of the information from the validator while generating this alloy model?
Yeah. Okay. Thanks for the questions. Let me answer them. I'll ask the second question first.
Okay.
The validator is a C++ program that consumes a SPIR-V binary file and either says, yes, this is valid, or this is invalid because it violates this rule of the specification or that rule of the specification. And the specification has got many rules that are unrelated to control flow. For example, you can't use an instruction ID that's not been defined, okay? Or in a graphics shader, you can't use certain features that are only allowed in compute shaders. So there are a number of things that validator checks that are irrelevant to our project. But it does check all of these control flow rules. So we were able to use the validator as an oracle to cross-check our model against by giving examples generated by our model to the validator and asking its opinion. We weren't able to use, so our modeling was informed by the validator's behavior, but I mean our manual modeling work was informed by it. There was no automated connection between our alloy model and the validator. Okay, and then I think your first question, sorry, I've forgotten the first of your questions. Can you repeat it?
Yeah. So first question was like, how big are these models in terms of?
Oh, yes. Yeah. Well, I forget how large the model was in terms of alloy code, but I think it ended up being a few hundred lines of alloy. But as with a lot of these things, that's not very informative because it took a long time to work out the right alloy. And in some cases, figuring out the right thing allowed us to delete a whole load of code we'd written, right? So I think the model kind of ballooned and shrunk as we converged on the right thing. I would say it took about, the project took about a year. And that was, when I was a Google engineer, I'd worked with SPIR-V for quite a while. So I started the project with a lot of SPIR-V expertise and a lot of ideas about the problems. The reason I did this project was that I had first-hand experience of the pain of this. So I came in with a lot of experience. The postdoc doing the work came in knowing nothing about SPIR-V and nothing about alloys. So there was the usual kind of learning curve for them. And that makes it hard to really estimate quite how much work there was. But really, this was a kind of expert project in the sense of we had to become experts in SPIR-V, experts in alloy, and there was a lot of manual work involved. So yeah, this is an example, I suppose, of using formal methods in earnest to solve a problem that, while it may not be the world's biggest problem, this really mattered to people who care about SPIR-V, and it was worth the time investment there. But it wasn't like an application of, it wasn't by no means a lightweight application of automated formal methods.
Yeah. No, it totally makes sense. Yeah. Thanks.
Any other questions? So also one quick question if we still have time. These were essentially sequential programs that you talked about, right? So were there issues with, control flow in, in parallelizing, in parallel constructs, which I'm sure must have been there, right?
It's a good question. So were there problems to do with control flow and parallelizing constructs? No, but what we did is indirectly related to that. The part of the reason for having these structured control flow constructs and structured control flow rules is to make it easy to implement GPU compilers. In a GPU, you've got instructions that allow barrier synchronization. They say that all of the parallel threads running in a particular work group need to synchronize at this point. They must all get here, and none of them can leave until all of them get here. And there are rules in the GPU world about where those barriers can be placed. You're not allowed to have multiple threads get into different barriers, or you can't have a situation where threads go around a loop and hit the barrier at having done different numbers of iterations of the loop, for example. So the control flow rules of SPIR-V are specifically designed to make it easier for compilers to handle GPU programs that use barriers in a correct way. So in some sense, data parallel programming with barriers is the reason for being of structured control flow. So although our work didn't involve directly working with parallel programs, parallel programming is kind of the indirect motivation for what we were doing.
Okay. Okay, so if there are no more questions, let's give Alastair a hand and say thanks.
Thank you very much. Have a good evening.
Yeah, thanks, Alastair. Great talk here.
Bye.
Bye.
Yeah. Let's close.